All right, guys. Before I really introduce the next topic, I want to start off with a bit of motivation. So, suppose that we had the following circuit. So the circuit itself, let's say, contains an independent voltage source providing us with 24 volts. This in turn is hooked up to a resistor there, independent current source providing us with 4 amps. Let's say there's another resistor here, and even a dependent source, let's say, at the top here. And let's make this a current source. That depends on a current Ix that's flowing down this way. This is an 8 ohm resistor, a 2 ohm resistor, and suppose that you actually had two terminals of interest here, A and B. Right? Now, one of the things that we're going to do is we're actually going to place the circuit inside a black box, like so, and make the observation that this network of independent sources, dependent sources, resistors, and everything, this is a linear network. Right? Now, one of the things that we can do is external to the terminals A and B here in our linear network. One of the things that we can do is we can actually place, let's say, a load resistor. And suppose that we made this a 1 ohm load resistor. One of the things that we can do is we can actually analyze the circuit and figure out what the voltage across the load resistor happens to be, how much current is flowing through the load resistor, as well as the amount of power that's being drawn from that linear network inside of that black box and delivered to the load resistor. However, notice that kind of a significant problem arises if, let's say, we change this load resistor from having a value of 1 ohm, let's say that we changed it slightly to a 10 ohm resistor, or maybe a 100 ohm resistor. When it comes to the circuit analysis techniques that you've developed up until now, each one of those problems is significantly different than the other. Every time you change out that load resistor, you have to go back and change all of the equations that you set down in order to analyze that circuit. So each problem is completely separate from the other problem as you're changing out that load resistor, right? So reanalyzing this entire circuit, especially when the circuit inside of the linear network is extremely large, it becomes a significant problem. And the question is, can we replace this big linear network circuit with another equivalent circuit that happens to be simpler than the one that we have there, so that every time we change this load, rather than analyzing the circuit with all of these other components, we can actually analyze that circuit in its simpler yet equivalent way. And it turns out that we can. We can actually replace any linear network whatsoever with what they call its Thevenin equivalent. So that's the topic for today. The topic is the concept of a Thevenin equivalent circuit. Now, given any linear network, so here, if I happen to have a black box, and within this black box, I have components like resistors, voltage sources, current sources, independent, dependent. Later on, we can extend it to have capacitors and inductors and op amps and all sorts of stuff, all sorts of goodies. And so you can imagine that this linear network is an extremely complex array of multiple components. It turns out, due to the fact that this is a linear network, no matter how complicated it happens to be, what Thevenin's theorem tells us is that we can replace it with a single voltage source that happens to be in series with a single resistor. The value of the voltage source is what they call the Thevenin voltage, and the value of the resistor is what they call the Thevenin resistance. Right? Now, really, truthfully, think about that. No matter how complicated this linear network is, I can replace it with one single voltage source in series with one single resistor. That's an extremely important simplification. So this entire circuit that's up here inside this linear network, right, I can replace with one voltage source that's in series with one resistor. And rather than analyzing this large circuit up here, all I have to do is replace it with a much simpler one, and then I can actually simplify my analysis greatly. So here, the goal, and this is the major goal, is for any given linear network, we want to find, first and foremost, well, what is the Thevenin voltage? And we want to find what is the Thevenin resistance, so that we can actually make those circuits equivalent circuits and do the replacement, make the replacement. Right? Now, there are multiple ways in which you can actually attack this problem. However, are two common circuits that we tend to look for, because again, remember, we have access to the given linear network. There are two common circuits that we look for that will allow us to find the Thevenin voltage and the Thevenin resistance such that we can replace that linear network with the Thevenin equivalent. And the two circuits that we're going to look at to find these, the first one is what we call the open circuit. And given the open circuit, one of the things that we're going to do is we're going to find what we call the open circuit voltage. And the second circuit that we're actually going to take a look at is going to be what we call the short circuit. And by looking at the short circuit, given the linear network, we're going to find what we call the short circuit current. And given these two parameters, we can then find the unique Thevenin equivalent to the given linear network. So let's see how to do that. Let's talk first and foremost about the open circuit. So for the open circuit, again, remember the linear network and the Thevenin equivalent themselves are going to be equivalent. So here I have my linear network like this. And my Thevenin equivalent consists of a voltage source in series with a resistor. Right? Now, one of the things that you can clearly see is if you happen to have an open circuit at the terminals A and B, right? Very clearly, you cannot have any current that happens to be flowing on the external side going from A to B, right? So the current that is flowing out this way happens to be zero. And notice that it happens to match with the current that flows out this way with the Thevenin equivalent, right? However, there is a non-trivial voltage called the open circuit voltage between the terminals A and B, like so over here. So over here, since these are equivalent circuits, there is an open circuit voltage over here that we can find. Now, this is the key. Given the linear network, we can find, not looking at the Thevenin equivalent, but we can find the open circuit voltage from the linear network. So here, this is something that as a problem we found. And you can use any technique of circuit analysis given the linear network. You can use any technique at your disposal in order to find that. So you can use the node voltage, mesh current, anything that you want. Right. Now, in terms of what we're looking for over on the opposite circuit, well, we know that the current flowing on the external part and going from A to B out here, well, that's 0. Why? Because it's an open circuit. That also means that the current flowing through the resistor is 0, which also means that the voltage across the resistor is 0. And this is again because this current is 0, right? And one of the things that I can do is I can define a loop around this. So I'm going to use KVL around the loop. So I'm going to add up the voltages around this loop, and they must add up to 0. If I start over here and I move around this way like so, well, I first encounter the Thevenin voltage, so into KVL goes minus the Thevenin. I then go through this resistor, but there is no voltage across it because there's no current. And then I go through the external side of that, and I'm going through positive open circuit voltage. That's equal to 0. Notice that I can solve for the Thevenin voltage, and that is equal to the open circuit voltage. This is the first result that we wanted. So if in the given linear network I can find the open circuit voltage that will be equal to the Thevenin voltage that I need over here to create the Thevenin equivalent. We then are going to look at the short circuit. So here we're going to take a look at the short circuit. So we're given the linear network, and it's the same one as previously, has two terminals A and B. Now, for the Thevenin equivalent, we do have our voltage source in series with a Thevenin resistor, like this, terminals A and B. And if I place a short circuit across this, there is going to be a certain amount of current that flows through there externally from A to B. This is what we call the short circuit current. And it is this, given the linear network, that we're actually going to end up finding. So we're going to find the short circuit current given the linear network. So it's something that we will find. It's something that we will have a value for. Now, in terms of the Thevenin equivalent, that means that over here, we're going to short circuit this as well, and there is going to be that short circuit current that flows externally through there. Right? And notice that this short circuit current, because the voltage source is in series with the resistor, right, it should be very, very, very clear that this short circuit current is equal to the Thevenin voltage divided by the Thevenin resistance, just by Ohm's law, or that the Thevenin resistance, just by rearranging this equation, is the Thevenin voltage divided by the short circuit current. But again, we found that the Thevenin voltage is the open circuit voltage divided by the short circuit current. This is the last piece of the puzzle that we actually needed. Let me write it out cleanly. That Thevenin resistance will be the open circuit voltage divided by the short circuit current. This was the second piece of the puzzle that we actually needed in order to find our original Thevenin equivalent. Now, keep in mind, this process is lengthy. It's not a simple process. In fact, whenever you actually go to one of the circuits, the linear network, and you find the open circuit voltage, you cannot use any result from that calculation in order to find the short circuit current. There are two separate circuits given the linear network that you will be using in order to find the open circuit voltage. That will be the Thevenin voltage, to find the short circuit current, and then based on this last equation, you can then find the Thevenin resistance. I know that it seems, again, like a lengthy process, but we will have plenty of examples that we can go through in order to show you how to go about finding the Thevenin equivalent. Thank you for watching, and I'll see you for the next video.